Preparing for interviews? I have a gift for you. 10 amazing questions from linked list that are being asked at hundreds of interviews tons of times. And there is a very clear reason for that. Linked list is one of the fundamental data structures, and it is very good indicator that to know that whether a candidate has good understanding of the fundamental concepts of computer science or not. That's why they remain so prevalent and so popular in tech interviews. You take any big, small, medium companies, they are for sure going to focus quite a lot in linked list, and you have to know this stuff. Today we are going to do a very interesting LeetCode problem called add two numbers. And if we see some of the popular companies who have already asked this question, there are companies like Amazon, Apple, Bloomberg, Microsoft, Facebook, Google, Uber, Paytm, TCS, ByteDance, Goldman Sachs, and Airbnb. So that's why I'm paying my utmost attention. I hope you also enjoy the video. This one is a LeetCode medium problem and also very well-liked problem. Basically, we are given two non-empty linked lists that represents two non-negative integers or two non-negative numbers. Now we are told that these digits are actually stored in a reverse order and we need to find the sum of these two values. So this is the whole problem. Basically, we are given just two numbers, n1 and n2, and we need to find the sum of them. So n1 plus n2, what is that going to be? And we need to the tricky part in this case is both of them are given in form of like linked list. So we are given linked list 1 and linked list 2 that represents both the numbers, and we need to add them and just create an answer linked list, and we need to return the head of this linked list. So let's try to understand this with an example, and that would make things more clear. So suppose over here we are given two linked lists L1 and L2. Now notice that the numbers represent are over here are 2, 4, 3, and this one is 4, 6, 5. But we are told that these are actually stored in the reverse order, which means that the least significant number that in a number system can be actually comes in the first position, which means that the actually this one represents the number 342. If we want to put it in the decimal system, same way this one represents the number 564. And now we need to do sum of these two values, and whatever the answer is, we need to store it in a similar linked list kind of a fashion in reverse order. So the logic is going to be quite simple. Let's try to understand this with an example. So basically in this case, the two linked lists are 2, 4, and 3. So this one is linked list 1, and linked list 2 is going to be 4, 6, and 5. Now if we want to do sum of these two and store it in the result, basically the answer is going to look something like this. So first of all, we are going to do sum of these two values, 2 and 4. So the answer is going to be 6. We can put 6 directly over here. Now in this case, the value are 4 and 6. So if we do 4 plus 6, basically the answer we get is 10. So 10 we cannot put directly as it is, because we can only store one single character in this kind of a block, which means we can only store 0 over here, and 1 is going to be a carry that will be forwarded over here. So let's just add one carry over here. So it's going to be 1 plus 3 plus 5. So it's going to be 8. And the answer is basically 806. But again, since we have stored it in the linked list fashion, the answer has been stored reversely, but the actual answer is going to be 806. And basically this is what we need to return. So this is a really simple problem to understand. So say for an example, these are the two numbers we are given. I'm also noting them over here, 708 and 503, and we need to do sum of these one. What is going to be the most simple logic that we are going to use? Now, given the fact that we are given these two as linked list 1 and linked list 2, the logic we are going to use is just a simple arithmetic, nothing more than that. The most basic approach that we have studied in second grade, this is what we are going to do. We are just going to do simple arithmetic. So the idea is that we are going to have a variable called carry that is going to keep track of that whether there is any carry that exists or not for any single pair of sum that we are going to do. That is one thing. Second thing we need to iterate over is until the possibility of whether we run out of both of these linked lists, because it could be possible that this linked list could be only of length 3 and this linked list could be of length 4. We might have an additional variable over here, something like 6, and basically this value is going to be 6503, but sum is going to be amongst these values and this value is going to be by itself. So we are only going to concern about this value plus the carry in case we need to do it. But since this is not the case, we are not going to do it, but I'm just letting you know that these are the possibilities that could exist. Now we know till what points we need to run, we know how to start, and we know what are the values we need to do the sum of. So the logic is going to be that we are simply going to create a new dummy node. So every single time we are going to create a new node. Now in this case, I know the answer is going to be this, so I directly created this, but typically we will only be creating just one dummy node, okay, at a time. And then we would do sum of these two values, and initial carry value is going to be 0. So initially this carry value is going to be 0. Okay, now let me get rid of these numbers, they are causing some confusion. So first we are doing 8 plus 3. 8 plus 3 is going to be 11. Since 11 is greater than 10, we are only going to put 1 over here, and we are going to change the value of the carry. Now carry can only have two values, either 0 or 1. Why? Because the maximum possible number we can get amongst two digits is always going to be 19. Why 19? Because the maximum two digits could be 9 plus 9, and we could have a previous carry that could be 1. So even if we do sum of all of these, it could only lead up to the value of 19. So there can only be two possibilities for the value of carry. So I'm just letting you know these things. Now in this case we have this value 1. Okay, now we are going to move to the next value. So if we move to the next value, basically this is 0 plus 0, but the value of carry is 1, so it's going to be 1 plus 0 plus 0. So the value is going to come 1 over here. Now again in this case, since we have already used this carry and we do not have anything, the carry value is going to go back to 0 again. Now we have the value 7 plus 5. 7 plus 5 plus 0, so that is going to be value 12, but the 12 is still greater than 10, so we are only going to put 2 over here, and we are going to have a carry that we need to go over. And now notice in this case, even though we ran out of both of these linked list and we do not have any more values to iterate over, we still have carry that is not 0. So again we are going to add one more node over here, and we are going to add the value of carry in this case, and that is going to be 1. So in this case the answer is going to be 1 2 1 1, and this is like the numeric sequence if we go in this direction. But since we are only needed to return the linked list, we can simply return this linked list as the answer, and this is the whole logic. So the problem is really simple to solve, easy to understand, and nothing more complicated. Time complexity in this case, the time complexity is basically going to be big O of maximum of either length of m or n, where m is the length of this one and n is the length of this one. So whichever is the maximum value, we need to iterate those many steps. So first of all, we are going to create a new list node called dummy node. This dummy node is going to act as a placeholder for our actual answer. Now we are also going to create a new list node called answer. We are also going to have a variable called carry, and the initial value is going to be 0. Now we are going to run our while loop, and inside our while loop we are going to keep on running until we have values in either L1 or L2, or the value of carry is not 0. Inside the loop, first of all, because these are list nodes, we will have to create two integer variables called x and y, where we will store the value of the subsequent list 1 and list 2 variables if they are not null, and if they are null, we are going to store their values as 0. We are also going to initialize a variable called sum, and we are going to do x plus y. We are going to calculate the value of carry, so for that we can only do sum divided by 10 and we will get the answer. Now for our answer node, we will have to add the value of the sum that we have calculated, but it could be possible that the value of the sum could be greater than 10, and we only need to store a single digit between 0 to 9. So what we can do is, we can inside the answer dot next, we can simply store the value of the sum modulo by 10. And now for the present pointer, we will need to update the pointer inside the answer list. So we are going to move to the next element, and same way we will also have to update the value of the L1 and L2 to move to the next nodes, but we will only do it if they are not null. Basically that's it. This is the whole meat of the operation, and now all we need to do is we simply need to return the value of the dummy.next, because dummy.next points to the first value where the answer node starts recording all the values. Let's try to run the code. We are making a mistake. So inside the sum, we are not actually adding the value of the carry, so we will also have to do that. Okay, seems like our solution is working. Let's submit this code, and our code runs decently efficiently compared to a lot of other solutions. So this is a very good approach. and I would be posting the solution in the comments so you can check it out from there. Hello friends, we are not employed by FAANG company, so let's not stop lead coding till we get there. Today we are going to do reverse linked list problem, and essentially this is a very easy but very important lead code problem, as it has been asked at bunch of different companies. So this problem has been asked in companies like Amazon, Microsoft, Apple, Bloomberg, Facebook, Google, Nvidia, Adobe, Uber, and also IBM, eBay, PayPal, other companies like Goldman Sachs, and then ByteDance, and a few other companies. So I'm paying my utmost attention. I hope you also enjoy the video. Hello friends, I got my results back from my Goldman Sachs interview, and I didn't clear it, which means that I have a long way to go, and I still have to do a lot of work on my coding and lead coding skills. This is a LeetCode easy problem, and it is one of the most liked problems on LeetCode. Basically, we are given a head of a single linked list, and we need to reverse the given list, and then we need to return the reverse list. So problem statement is quite easy to understand, and even if we see the example is also quite easy to understand. Basically, we are given a list like this: 1, 2, 3, 4, 5, and we are at this position, and we are given this head value of this linked list, and basically we need to return the reverse list. So in this case, the reverse list is going to be 5, 4, 3, 2, 1. So essentially we are just iterating over in this direction, and this is what we need to return. The thing is, there happens to be a little bit more complexity, because we are told that this is a single linked list. So in single linked list, all the elements are just stored in a single manner, which means that this element only knows that what elements comes after it. It does not know that what is the element before it that is pointing to this position. So this is the concept of a single linked list, and we'll see that how can we solve this problem. Okay, so we need to reverse the linked list, and we are told that the linked list we are given is actually a single linked list. The thing is that what is the property of a single linked list? That every node in the given linked list actually has the value of that particular node, and also has the pointer towards the next node inside the linked list. And whenever we encounter that next node is actually pointing towards null value, we can determine that this is the end of the given single linked list. The issue over here is that we know that at any single position, what is the value after it using this next pointer, but we don't know that what was the value before it. There is no way for us to identify this particular item, which means that our aim is to find that how to reverse this linked list. And in order to reverse this linked list, what we can do is, rather than pointing towards the next pointer, we can, if at any given position for all the nodes, if we just point it towards the reverse direction, and basically start our linked list traversal from the last node, we can simply return the reverse linked list immediately. And this is the approach we are going to take. Now the question comes that how at any point we can actually, originally we were pointing on this side, how can we start pointing on the reverse direction from any single node? And in order to do that, what we'll have to do is we'll have to keep track of the previous character or previous node as well, and apart from keeping track of the current node. So the approach we are going to use in this case is that every single position, suppose we are at this element, so this is the current element we are at, right? From this current element, we know that how to get to the current dot next, or which means that how to go to the next element, we already know that. The question is, we don't know that how to go back. So what we are going to do is, we are going to keep track of a previous character or previous node that will always be behind this current node. So in this case, this would become our previous node, and all we will have to do is that over here, the current dot next is actually pointing towards this node 3. So rather than current dot next pointing towards this node, we are going to have current dot next point towards the previous element, and we are going to do iteratively for all the values. So initially at the beginning, this would be our previous and this would be our current. So over here, this value will be pointing towards this on this side, so null value. Now again, we will switch our values for previous and current. So this would become our previous and this would become our current, and again we will flip the value. and again we will repeat the same process. So this would become our previous, this would become our current. Again we will flip the direction, and at the end this would become our previous. And if we see the previous dot next element, it would be a null sequence, so we would know that okay, this is the end of the original linked list, so this has to be the start of the new linked list. And then we can just start iterating over, which means that we would have taken care of all of these pointers, and now we can simply return the reverse linked list in this fashion, and this would be our answer. So if we see the time and space complexity in this matter, the time complexity for this one would be big O of n, and the space complexity would only be big O of 1, because at any given position all we have to do is just keep track of couple of variables, nothing more than that, and that should take care of all the scenarios. So first of all, we are going to create a new list node, and we are going to name it as previous, and we are going to initialize the value as null. And we are also going to create a list node called current, and we will have it start at the head value. Okay, now we are going to iterate over the given linked list. So while current is not equal to null, we are going to keep running in the loop. And inside the loop, essentially we have to flip the values between current and previous. So what we can do is current dot next would be our previous node, and then for the previous node we will have to flip it to current node, and for the current node we will have to go to the next node in the original single linked list. So for that we will have to create a temporary variable. So let's create a new node, and we are going to name it as temp, and we are going to store the current dot next node over here. And now for the current node we are going to point it to this temp, because remember over here we are updating this current dot next value, so that's why. Okay, and yeah, I think this is it. After this loop ends, we should have our linked list reverse, so we can simply return the head as previous variable, and this should be it. Let's try to run this code. It seems like our solution is working. Let's try to submit the code. Okay, our code actually runs 100% faster than all the other solution, because it's running in constant time, and I would be posting this in the comments. You can check it out from there. Thank you. Hello friends, we are still not employed by FAANG company, so let's not stop lead coding till we get there. Today we are going to do linked list cycle problem. So basically it is a problem to detect cycle inside the linked list, and this problem has been asked by a bunch of different companies. So let's see that what are my dream companies that have asked this problem. It contains the companies like Amazon, Microsoft, Shopify, Goldman Sachs that we recently got rejected at, Google, Bloomberg, Apple, Facebook, Yahoo, Splunk, and eBay. So these are some of the companies that I'm really interested to get a job into, and that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode easy problem, and it is really simple to understand. Basically we are given the head of a linked list, and we need to determine that whether this linked list contains a cycle or not. Now first of all we need to understand that what is the property of a linked list. Basically inside the linked list we are given two items. First item, we are given some data point that represents that particular node inside the linked list, and we are given the information about the next node inside the given linked list, and that is how linked list keeps on progressing. So we will keep this in mind. Hopefully everyone should be familiar with this one. And now the question is that we need to determine that whether inside our given linked list does there exist a loop or not. So suppose we are given a linked list like this, and in this case we can clearly see that there exists a loop between this 4 and this 2. The question is that how do we detect that there exists a cycle? And first solution that comes to mind is the solution that we have been using at different graph and some other problems. So basically what we can do is, at any moment we are given this head position. So what we can do is we can create another data structure called hash set, and inside this hash set we are going to keep track of all the visited nodes that we have passed so far. And what we are going to do is, initially, first of all, we are going to check that whether at any given node we are currently at, if that exists inside this visited hash set or not. If it does not exist, we will add it to this visited hash set and we will keep moving forward. So at any moment, if we encounter the same node, we can clearly determine that there exists a cycle. So in this case, first of all, we will check that whether this one exists in the visited hash set. It does not exist, so we will add 1 over here. Then again we check for 2, 2 does not exist, so we will add 2 over here. Then again we check for 3, 3 does not exist, so again we add 3 over here. And again we check for 4, so 4 also does not exist, so we will add all 4 entries. Now from this 4, the next value it points to, it actually points to this value number 2. And whenever we check that whether this 2 exists or not, we can clearly see that 2 exists over here, and we can immediately say that because we came back at a node that we have already visited before inside the hash set, we can determine that there exists a cycle. And in this case, we will return true, that okay, yes, there exists a cycle over here, and that would be our solution. Now this solution is perfectly fine, it works okay. If we calculate the time and space complexity, the time complexity in this case is going to be big O of n, because we are iterating over all the nodes just one time. And the space complexity in this case would be big O of n as well, because we are using this additional visited hash set to detect that whether there exists a cycle or not. The next thing that your interviewer is going to do is, he is clearly going to ask that solve this problem without using this additional additional space, and the space complexity should be big O of 1. So let me show you the most optimal solution where the space complexity would be big O of 1 and time complexity would be big O of n. I have a short announcement. I have recently created a GitHub repository. The link is in the description, and I will quickly show it to you as well. So this is the repository that I was talking about, and I have left it public so anyone can access it. It contains list of solutions of all the LeetCode problems that we have solved so far. So you can click on any problem and you can go to its solution, and it will contain the Java solution for that particular problem that is acceptable at LeetCode. Our aim is to see this list growing, and I would be posting all the solutions that I solve, and hope it helps other fellow coders. And our aim is to get into FAANG, and hopefully this can be a big stepping stone towards that direction. Basically what we are going to do is, we are actually going to have 2 pointers that iterate over this given linked list, and we are going to have a slow pointer and a fast pointer. And the aim is that at any moment this fast pointer is always intended to stay ahead of the slow pointer. And if we identify that this fast pointer actually reaches back to the slow pointer, we can determine that there exists a cycle. Let me show you how. So what we are going to do is, we are at this head position, so we are going to first of all initialize our slow pointer and our fast pointer at these positions. So slow pointer would be at the first position and fast pointer will always start at the second position. Now we are at this position, we are going to have one more condition, that slow pointer will always do one jump. So slow pointer will always do slow plus 1, so it will always go to next node. But for the fast pointer, we are actually going to have fast pointer do two jumps. So fast pointer is going to do fast pointer plus two node jumps. And let's see that how things will turn out in this case. So initially we are at these positions. Now this first pointer makes 2 jumps and slow pointer makes 1 jump. So their corresponding position change. So slow pointer will reach over here, and meanwhile fast pointer actually made 2 jumps. So fast pointer will end up over here. Now in the next case, the slow pointer again is going to make 1 jump. So slow pointer will reach over here, and this fast pointer is going to make 2 jumps. So fast pointer will make 1 jump over here, and second jump it will reach over here. So in this case, fast pointer will also reach at this place, and slow pointer also reached at this place. So over here we determine that this value at this fast is equal to value at the slow node. And because we identify this condition, this can only happen true if there existed a cycle somewhere. And because there existed a cycle, we are able to determine that okay, there exists like this fast and slow reach at the same point, they met at the same node. So that's why there for sure there has to be a cycle. What happens if there does not exist a cycle? So say for an example, in this case, again let's just go back to this scenario that okay, this is the list we are given, and there does not exist a cycle. And let's add one more node over here. We'll just name it number 5, and this is the whole linked list we are given. Now in this case, again, this is the slow pointer, this is the fast pointer, and we are always going to have a terminating condition that either if slow reaches at the end or if fast reaches at the end, at any given moment we reach to the end of the list and we find that the value of this slow or fast pointer is actually null. If that is the case, we can determine that we are able to successfully traverse over the entire linked list without detecting a cycle, and that would be our final solution. So in this case, slow is here, fast is here. Let's make one jump. So again, so now the slow would be here and fast would actually be here. Now again, let's just make one more jump. So in this case, slow would be here, but fast would have already crossed this portion. So fast would be somewhere over here. The node is null, which means immediately we can determine that because we find that the fast pointer was at null value, that there does not exist a cycle in this case, and we will return false in this scenario. So this would be the most optimal solution for this problem. It is very easy and very trivial to understand as long as you get this trick. And if we calculate the time and space complexity, the time complexity would be big O of n, because in any case we will have to iterate over all the nodes. In terms of space complexity, apart from using couple of additional variables, we are not using any more space, so we can say that the space complexity is actually constant time big O of 1, and this would be the most optimal approach. Okay, so first of all, we are going to check that if the given head is equal to null, we are going to return false. So this would be an edge case that we took care of. Now we are going to create two list nodes. One is for slow, and we are going to initialize it to the head position, and second one is fast, and we are going to initialize it to the second position. Okay, now we are going to run a while loop, that while slow is not equal to null or fast is not equal to null, we are going to keep iterating over. And we are going to check that if the fast.next element, if that is null, we can also return false immediately. If that is not the case, if at any point we identify that the value at fast is equal to value at slow, if that is the case, we can immediately say that there exists a cycle and we can return true. Otherwise, we will have to update the counter. So slow would be slow.next. So because we are incrementing slow by one value, but for fast, we are actually incrementing fast by two values. So fast would be fast.next.next. And that's it. And if at any moment we are able to get out of the loop, we can always return false. And this should be the solution. Let's try to run the code. Okay, seems like our solution is working. Let's try to submit the code. Oh, okay, we are going to check that if fast is equal to null or fast.next equal to null. Okay, seems like our solution is working, and it's actually pretty fast. It's actually it runs in 0 milliseconds, so 100% faster than all the other solution. And even in terms of memory usage, we are beating out most of the people, because over here we are actually ending our loop early by using both these conditions. And again, inside the GitHub, I will be providing the solution to all these problems, so you can go and check it out over here. I would be posting this link in the description, and hope this video helps all the other communities that I feel so dear for. And not stopping till we get into FAANG. See you next. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do a linked list problem called merge to sorted list. So this problem has been asked in tech giants like Amazon, Facebook, Microsoft, Apple, Uber, Google, Bloomberg, ByteDance, which is TikTok, and then companies like Yahoo, LinkedIn, Indeed, and Roblox, and also IBM. Plus recently in news, Twitter. So I am paying my utmost attention. I hope you also enjoy the video. This is a LeetCode easy problem, and it is also one of the most liked problems on LeetCode. If we understand the problem statement, we are basically given the heads of two sorted linked lists, list 1 and list 2, and we need to merge these two linked lists in one single sorted list. So this is the important part, that it has to be sorted, and in the end we need to return the head of the merged linked list. Okay, let's try to understand this problem with an example. So over here we are given two lists, list 1 and list 2, and we can see that both of them are increasing in ascending order. And now we need to create a merge list from this. So this is the merge list that has been created. Even if you observe the merge list, the ascending property is maintained. So which means that the merge list is also sorted. And how it is sorted? It has taken values from whichever the nodes that had the smaller value. So in this case, these first two values were 1 1, so we can choose from anyone, right? Now this second value, and now we are done with this value 1 and 1 over here. Now we need to take care of this 2 and 3. So when we compare this 2 and 3, we find that okay, this value number 2 is actually smaller, so that's why we add a 2 node over here, and now we are done with this one. And now we still have to compare this 3 with this 4, because remember, we are not done with this 3 yet. So we identify that this 3 is actually smaller. So in this case, we are done with this 3, and we add the 3 node over here in our merge list. Now the values are 4 and 4. So again, we just enter the values 4 and 4, and now we should be done with all of them. And this is the new list that we have created. And in the answer, we need to return the head value. So we would be returning this value as the part of the answer. So this is the expectation of the problem. Let's see that what could be the potential solution. So let me quickly draw just one more list, and we'll see that what should be the approach. Let's see that what should be the merge list at the end. So I'm denoting this as M. Now we are going to compare two values at any given moment, and we are going to have two pointers. So let's say left 1 and left 2, we are going to keep track of them. So over here both the values are same, so we can enter any value. So we will add 1 over here and then again 1 over here, because both the values are same, so you can put condition to choose anyone. Now we are done with both of them, and because we are done with both of them, we will have to update the values of this L1 and L2. So we are going to update its values. So now this becomes our L1 and this becomes our L2. Again we do the comparison. Now in this case we find that okay, this value is actually smaller. So because this value is smaller, we are done with this element. Essentially we will add that value to our merge list, and because in the list 2 we found that that value was smaller, we'll update the list 2 pointer to go to its next element. So we'll do a jump like this, and now this becomes our list 2, and again we will compare list 1 and list 2 elements. So in this case we find that value at list 1 is actually smaller, so we'll add it to our solution, and again we are done with this one now. So we'll update the left 1 pointer. So left 1 pointer would fall over here, and now again we will compare both of these values. So in this case we find that okay, this value is actually smaller, so we'll add one more node to our merge list 4, and again update the value of list 2. So list 2 actually goes over here, and this is done. So this is list 2, and now we compare this value with this value. So over here we would find that okay, this 5 is actually smaller, so now we will have to update the value 5 over here. Now because we have updated the value 5 over here, if we do a next jump for this list 1, we identify that this node is actually null. So the moment we identify that there exists a null node, there is no point of us moving forward in this direction, because we are done. And essentially whatever the remaining values are still pending in the L2, they directly needs to be appended on this merge list. Why? Because so far all the elements we have entered, they were entered based on the some sort of relative comparison. But once we are done with one loop, there is nothing for us to compare. So because there is nothing for us to compare, whatever is the remaining portion we can directly add over here. So we'll over here we only have one node 8, so we'll directly add the node 8 over here. But even if we had some other nodes over here, they all would be directly appended without any issues. I hope this makes sense, and this actually would be our final solution. Now what would be the tricky part in this one? The tricky part in this one would be that because in this merge linked list we are iterating over here, so at the end we would be somewhere at the last position. And remember, we need to return the head node. So what we will do is we are going to use a trick. We'll create some dummy node, and this dummy node would be actually as the head node. We will just assign some random value, whatever, 1 2 whatever. This does not make any difference, and the next value of this would be pointing to the merge dot next, and that would be the trick. So at the end we will just return the next value of this dummy node, and then that would be the start point of our merge list. So if we calculate the time and space complexity, in this case the time complexity would be big O of n actually, because we will have to iterate over all the nodes that are given in both list 1 and list 2. So actually it would be big O of m plus n, where m is the total number of nodes given in list 1 and n is list 2, but in general we can write it as big O of m plus n. And in terms of space complexity, we are only using couple of extra parameters to store the value, and anyways we will have to create this merge list, so we wouldn't consider that to be an additional space being used. So we can say that we are actually solving this in constant time, and this would be the most optimal solution. So first of all we will create a list node, and we will just call it as dummy. And for this dummy node, actually we are going to use this dummy node to keep track of the first element inside our merge list. Now we will create another list node, and we will call it as a merge list. So let's just call it merge, and we are actually going to initialize it with dummy value. And now we are going to run a while loop. Now we are going to run a while loop up until the point that when we have elements in both list 1 and list 2. So at any point we encounter that list 1 or list 2, either of them is empty, we are going to break out of this while loop. And inside the while loop we will have to check that which one is a smaller value, and suppose list 1 is smaller than list 2 value. So in that case we will have to add it to our merge list. So now we will add the value to merge list, but we are actually going to add it to the next element inside the merge list, and you will come to know that why we are doing it. So let's just do that. And now we will also have to update the value of list 1. So this should be list 1, and now let's update the value of list 1. Okay, and if that is not the case, which means that we will have to add the value from list 2. And after we break out from the loop, we will actually have to see that which list still has values remaining, because remember, at any point we encounter null in any either list 1 or list 2, we break out of the loop, which means that there could be still more elements that needs to be appended to this merge list, and that should be taken from whatever the list that is still not empty. So we will just put a condition: if list 1 is equal to null. If that is the case, we know that we will have to append the value of list 2. And if that is not the case, which means that list 2 is empty and list 1 still has elements, so we will add list 1 to our merge list. And once that is done, we need to return the head of this merge linked list. But the problem is that now we are actually at the end of this merge list. So how can we get the head of this? Well, actually we can get the head of this is by using this dummy node that we created, because remember that dummy is actually the start value of 1, and dummy dot next would be the value of merge dot next. So that's why we actually have to create this additional node. And in the return we are actually going to return dummy dot head, and dummy dot next, and this should give us the head value. So let's try to run this code. Okay, looks like we made some mistake. Oh, we are not updating the value of merge element, because at every iteration the merged node also needs to go to the next element because we are already adding a one value to this merge linked list. So now let's try to run the code. Okay, seems like our solution is working as expected. Let's submit this. And our solution is actually 100% faster than all the other Java solutions. So hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do merge k sorted list problem, and this is one of the most asked linked list problem. And if you just see that the number of companies that have asked this question is really huge. There are companies like Facebook, Amazon, Microsoft, Google, Apple, ByteDance, LinkedIn, Bloomberg, TikTok, and more companies like Uber, Goldman Sachs, Lyft, Twitter, Yahoo, Wish, Plantier, Tesla, Roblox, Pinterest, Airbnb. So these are my dream companies, so that's why I'm paying my utmost attention. I hope you also enjoy the video. This is a LeetCode hard problem and it is one of the most liked problems on LeetCode. But in my opinion, this should have been a medium problem, and I'll tell you why. Now, if we understand the problem statement, basically we are given k distinct linked lists and each linked list is sorted in ascending order. In the answer, we need to merge all the linked lists that are given in one single sorted linked list and then return that merge linked list. So this problem is very similar to a previous problem we did, merge two sorted lists. So you can find that solution over here. And if we see the example for this case, basically we are given bunch of different linked lists and all of them are sorted. So if we see this first example, we are given linked list like, now we need to merge all of them in one single linked list, and that single linked list needs to be sorted. So if we see the answer in this case is going to be that, okay, the smallest values are 1 1, so they will always come first, so it would be 1 1. Then we will have 2 3 4 4, so 2 3 4 4, and then we will have 5 and 6, and this would be the answer that we need to return in this case. That is the combination of all three linked lists. Basically in the brute force, what we can do is we are given few distinct number of lists, so it could be like list 1, list 2, list 3, all the way up to list k. These are the list we are given in the input. What we can do is, whatever the number of nodes they have, we can take all of those nodes, we can combine all the nodes, we can put it in a giant list. Let's just name it as merge list. In the merge list, initially we put all the values together once, and then all we need to do is, if we just sort this given merge list, then the sorted list would be our answer. And basically that's the whole solution. This solution would work perfectly fine, and then in the end we can just return whatever the sorted list we have found. Okay, what could be the issues with this problem? Like I won't find too many issues because this is also a decently good enough solution. If we see the time and space complexity, in this case the time complexity is going to be big O of n log n. Why n log n? Because initially we will have to do big O of n work to iterate over all the nodes inside the given linked lists, different linked lists, and merge them together. So that takes an big O of n time, and plus it takes big O of n log n time to sort the given list. So overall we will write them as big O of n log n. And in terms of space complexity, the space complexity in this case is going to be big O of n, because we need additional room to space to store one additional parameter of all the merged list before we sort it. Let's see that what could be another solution. So in terms of the second solution, suppose we are given three different lists like this. In this case, k is equal to 3 because we are given three distinct values. What we can do is, at any point we can denote three different pointers to each location. Let's name them L1, L2, L3. And what we are going to do is, our aim is to find the minimum value. We already know that for these three values, all the values are already in ascending order. So the approach that comes to mind is, okay, let's just create our merge list, and inside the merge list at any point we are going to compare all the values between this L1, L2 and L3, and whichever is the smallest we are going to pick that one. So in this case, okay, the smallest value is 1, so we'll pick 1 over here, and then we will update the value of L1. Okay, so this is already done. L2 and L3 will still remain same. So now we have these three values that we need to compare. So the smallest value is 2. So again we will update the L2, and this we are done. So now we have these three values to compare. So now again we'll add value number 3, and then we will be done with this one, and we'll update the value of L3. So let me just do it, do the whole thing, and hope you would be able to understand that how am I doing it. Okay, so this is how we will progress, and this would be our final merge list. So we can simply return this one. So this approach also works fine. There are no issues with that. If we see the time and space complexity in this one, the time complexity actually becomes, so suppose if we consider that all the elements in this L1, L2 and L3, the total number of nodes are given n. So we can say that the time complexity is going to be big O of n times whatever this k is given. So in this case k is 3, so we can do n times k, so it's going to be n times k, and this would be the time complexity. So why n times k? Because remember, in order for us to enter any single element, we will have to do k work. We will have to compare all these three elements, and at any point we find the smallest element, we will have to update that value. So suppose if k is equal to 1000, then we might have to compare 1000 elements at once. So that adds a little bit of complexity to it. So is this approach good? This approach is okay, but not very good, because as I mentioned that if we are given million elements as k, then basically what we are doing is just big O of n square work, while we already know that even in brute force we are able to solve this in big O of n log n. So why do we need to do n square work? Okay, so there is no point in doing that. Let's see that what would be the most optimal solution. Okay, so suppose we are given three lists like this, and I know you are thinking that why I only put two elements in each list. I'll just show you why. Uh, Basically, what is our aim? Our aim is to find that all the nodes that should be merged, and that merge list has to be in ascending order, right? We need to maintain this ascending order. So one of the best thing that should come to your mind is that, is there any data structure that already exists where no matter how many number of elements you put inside it, whenever you start taking the elements outside, they should be following this ascending order property? And yes, there exists a predefined element or data structure that can do it, and that name is actually heap. So if we maintain a min heap in this case, if we add all the values inside the min heap and then we start taking values or the nodes outside of the min heap, it is actually going to give us the sorted list, where it is the combination of all the merged elements. Let me show you how. So let's create a priority queue that will represent this min heap. Okay, and now let's start adding elements one by one. So first we will add 4 and 7. Okay, next element is 3. So the moment we need to enter 3, we will have the priority queue is going to fix itself. So now it is going to be 3 4 7. Okay, now we need to enter 8. So 8 we can enter over here. Now this node we have to enter is 1. So again, when we need to enter the 1, the priority queue is going to adjust itself. So now the solution is going to be 1 3. And the last node we need to enter is 11. So this, we have all the elements inside our priority queue. And now because we have this priority queue setup, what we can do is now we can start polling all the values from the priority queue, because remember, the property of priority queue is that all the values are entered at the back and they gets out from the front. So now we will create a new merge list. Now inside this new merge list, all we need to do is just keep on adding all the elements that are coming out of this priority queue. So sequentially we will be adding 1 3 4 7 and all those elements, and this would be the final solution that we need to return, and we can simply return this as our answer. And this would be the most optimal approach. Like this is there are other approaches that work in the same time and space complexity, but why this would be an optimal approach? Because your interviewer would like to hear that, okay, you are aware about this min heap concept and you can use priority queue when needed. So this sounds reasonably fine. If we see the time and space complexity, in this case the time complexity is going to be big O of n log n. Why n log n? Because in order for us to enter all the values inside the priority queue, it takes a log n time, and we need to do it for all these n elements. And in terms of space complexity, the space complexity is going to be big O of n because we need to use this additional priority queue. And let's see the coding. So first of all, we will initialize a priority queue, and let's name it min heap. So now we are going to run a for loop, and we are going to iterate all the lists and all the nodes, and we are going to keep on adding those inside our min heap. And after adding the value to the min heap, we will have to update the value of list as well. So we'll do list is equal to list.next. Okay, so after this loop ends, all the nodes should be inside our min heap, and now what we need to do is take all the elements out of the min heap and put it inside our merge list. So first of all, we are going to create a dummy node that would act as a placeholder so that we can call our head when we need it. And this is the same trick we use in previous videos as well, so you might be aware of it. Once this is done, we will create our list node called merged list, and for the merge we are going to assign the first value as dummy, so that in the future we can call this dummy node to find the head of this merge list. And now we simply need to run a loop that while there exists an element inside the min heap, we will have to add all those elements to our merge list. And once this is done, all we need to do is just return the dummy.next. And this should be our solution. Let's try to run the code. Okay, seems like our solution is working as expected. Let's submit the code. And our solution works pretty efficiently, as you can see. And I would be posting this solution inside the comments, so you can check it out from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop LeetCode until we get there. Today we are going to do remove nth node from an end of the list problem, and this problem can be asked in many different ways. And if we see some of the companies that have already asked this question, it's really nice. So companies like Facebook, Amazon, Microsoft, Google, Bloomberg, Uber, Apple, ByteDance, Goldman Sachs and Salesforce, they have all asked this problem, and they are some of my dream companies that I want to work at, so that's why I'm making these videos. I hope you enjoy them. Let's try to understand the problem statement. This is a LeetCode medium problem, and the title of the problem actually is self-explanatory, that essentially we are given the head of a linked list and we need to remove the nth node from the end of the list and then return its head. So this is the whole problem. If we try to understand it using an example, in the example originally we are given a list called 1 2 3 4 5, and over here we are given that n is equal to 2. So we need to remove second node, but remember we need to remove the second node or nth node from the end of the list. So in this case, this would be the first node at the end of the list, and this would be the second node at the end of the list. So we will need to remove this 4, and once we remove this 4, the answer would be something like this. So this is what we need to return, and in this case we will need to return this head pointer, and then automatically it will traverse towards the entire linked list. Okay, so let's see that what would be the most basic solution to solve this problem. Suppose we are given a custom example like this, and we need to remove second node from the end of the list. Now in this case, this would be the first node from the end of the list, and this would be the second node from the end of the list. So we know that we need to remove this value number 5. But the thing is, we are able to know it because I have drawn in the picture over here, and it is very evident to us. But actually we don't know that what is the length of this given list. So because we don't know the length, what we need to do is that the answer is quite simple. First we need to identify that what is the length, and then we need to, based on this given value n, we will need to determine that what is the element that we need to remove, and then it becomes easy for us to remove the element. So what we are going to do is we are going to use a 2-pass approach, and inside the first pass we are just going to have a variable called n, l, and this L is to take care of the length of this given linked list. So in this case we would find that okay, length is equal to 6 because there are 6 nodes present in this given example. Now once we know that there are 6 nodes present and our given n is equal to 2, we will need to remove the 5th node. Why fifth node? Because the node we need to remove, that is going to be determined based on the formula that total length minus whatever the n is given plus 1. Why plus 1? Because we are using one index calculation over here, that this last element, this sixth element, is also the first last element. Remember that this is the critical part, that this is the first last element, which means this is the second last element. And because of that, if we see over here that this L is equal to 6, this N is equal to 2, so 6 minus 2 plus 1 becomes 5, and that's why we determine that we need to remove fifth node. If we don't do this plus 1, essentially 6 minus 2 would be 4, and we don't need to remove fourth node because fourth node is actually third node from the end of the list. So that is why I gave you this long explanation. Now in the first pass we determine that okay, this is the node we need to remove, that this fifth node we need to remove. So all we need to do is in the second node, in the second iteration, we are just going to iterate over this given list again till we reach the fifth node. So the moment we find that okay, our current node is fourth node, which means that the next node is fifth node, right? So all we need to do is that whatever the fifth dot next is pointing, so currently fifth dot next is pointing to this value number 6, we are going to append this value to this fourth dot next. So rather than over here this 4 pointing to this 5, we are going to remove this link and we are going to make this 4 point to 6, which means that this 5 is automatically removed from this given input list, and that would be our solution. But the moment you present the solution, your interviewer is going to say that rather than using two pass system, suppose we want to complete this whole thing in just a single pass, in just a single iteration, then what should be your approach? And this is the critical part. So let me show you that what would be the most optimal solution. Let's use the same example, and inside the same example, first let's try to understand a couple of things over here. Suppose over here in this case we are told that remove n is equal to 1. So how can we determine that n is equal to 1 is which element? We can determine that okay, this is the first element from the end of the list. Why? Because the very next element of this one is actually null, and this is the key point, which means if we are given that n is equal to 2, so which means we need to remove the second element from the end of the list. So how can we determine? We can determine it by saying that okay, currently if we are at this position, the second node from this one, so next to the next node would be a null node, and if that is true, we can determine that okay, this is the second node from the end of the list. And this is a very important property that we need to identify. So basically what we are going to do is we are going to use two pointer system over here, and inside the two pointer we are going to have a back pointer and a front pointer, and the position of this back pointer and front pointer is determined based on whatever this n is given. Say if our back pointer is going to be at this position, which means our front pointer needs to be 2 steps ahead. So 2 steps ahead from this back position would be 1, 2. So this is where our front pointer would be at the beginning, right? And now since we have both of these positions set up, all we need to do is just keep iterating to the next element, and we are going to iterate until we find that this f or the front element is actually at this null position. So let's see that what would be the different pointer situation. So now our back pointer is come to this position, and again our front pointer is going to come to this position, because back pointer jumped from here to here and front pointer jumped from here to here. Again front is not at null, so again we will have to do one more iteration. So now the back pointer will come over here, and the front pointer will jump to one more step, and front pointer will come over here. Again front is not null, so again our back pointer is going to take one more jump, and our front pointer is also going to take one more jump. So front pointer will come over here, and over here we've identified that this front pointer is at null position. So this is the critical point. Now this front is at null position, so we have identified that okay, now this back pointer is exactly enough spaces behind it that whatever the next node is, that needs to be removed, and that is what we are going to do. So over here we identify that okay, this back is at correct position. Now what we need to do is currently back dot next is the point that we need to remove. So what we are going to do is simply we are going to point this current back.next. So current back.next is this 5 value. We are going to point it to whatever the back.next is, and this would be the solution, because back, what would be the back next, it would be this one. So rather than this 4 pointing to this 5, we are going to break this link, which means that there is no way for us to reach to this 5, and now 4 is directly connecting to 6, and then we need to return the solution. Now we need to return the head of this linked list. So we are going to use the same point we have been using so far, that initially we are going to create a dummy node, and this dummy node is going to act as a placeholder, and that is going to store this head value, and we are going to return that in the solution. And let's see that what would be the time and space complexity in this case. So for the time complexity, it's only going to be big O of L, where L is the given length of the linked list, and in terms of space complexity, we are only storing a couple of parameters, so it would be constant time, and so we are not using any additional space. So first of all, we are going to create a dummy node, and inside this dummy node we are going to give it some random value. We are going to create dummy dot next equal to head, and we are using this dummy node as a placeholder. Now let's create our two front and back list nodes. Okay, once that is done, now we will need to bring the front node n steps ahead of the back node. So we are going to run a for loop. After this loop ends, the front and back are at the current position, so now we only need to run a while loop till the front element is not equal to null, and all we need to do is just increment the value of front and back elements. And once that is done, now we are at the correct position for back to remove the next node. So we are going to do back.next equal to back.next.next. Okay, and now we have removed the node, that the nth node from the end of the list, so we can simply return the head of the list, and this should be our solution. Let's try to run the code. Okay, seems like our code is working. Let's try to submit the code, and our code runs pretty efficiently. I will be posting the solution in the comments, so you can check it out from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop LeetCoding till we get there. Today we are going to do reorder list LeetCode problem, and solving this one problem is actually equivalent to solving 3 different LeetCode problems, and I'll show you how in this video. So if we check out the list of companies that have asked this problem, there are tech giants like Amazon, Microsoft, Adobe, Facebook, Bloomberg, Uber, Google, Yahoo, Apple, eBay, Lyft, and Expedia. And these are some of my dream companies, so that's why I'm making these videos. I hope you also enjoy the video. So this is a LeetCode medium problem, and basically we are told that we are given the head of a singly linked list, and we need to reorder this linked list and return in a different manner. So let me quickly show you by an example that how do we want to return it. So suppose we are given a linked list like this, that 1, 2, 3, 4. This is a normal linked list we are given, and now we need to reorder it in a manner that one node we take from this left to right direction, and the another node we take from this right to left direction. So in this case, the first node is going to be this one, this node number 1. And now once we have taken this node from this left to right direction, the second node we are going to take is from the opposite direction. So second node in this case is going to be this value number 4. So second node would be the value number 4. Again, since we have taken node from the end of the list, so next node we are going to take would be this one, the value number 2. So again we will take a node this value number 2, and now at the end we will continue in the reverse fashion, and the next node we will take would be value number 3. So this would so this is the sequence we would need to return in this case after all the nodes that we have taken. Now let's take one more example. So again in this case we will take one node from this left to right and one node from this right to left. So the first node would be node number 1. Second node would be node number 5. Then again next node would be node number 2. Then again next node would be node number 4, and then again next node would be node number 3. So in this case, this would be the sequence that we will need to return as the result. Suppose this is the linked list we are given and we need to reorder this linked list. So what is the approach we are going to use? Basically, we need to understand that what are the things we need. Well, we need all the nodes that are going from left to right, and we are also need all the nodes that are coming from left to right. But the critical part is that this is a single linked list, which means we don't have any way to move in the reverse order. So what we are going to do is, first of all, we are going to create a reverse linked list, and then we are going to merge it with this original input. And the second linked list we are creating, we are going to create it smartly. So this is the input we are already given, right? So we already have our first linked list that we need to create, which is this one. What we are going to do for the second linked list is, for the second linked list, actually for this original given input, first of all we are going to find what is the middle of the linked list. So in this case, the middle of the linked list is going to be this node number 4, and the sequence starting from this node to 4 5 6, this is going to be the middle of the linked list, right? So in this case, the first linked list we have is, and for the second linked list we are going to choose it from this middle node. So the second linked list would be, okay, now we have for both our linked list first and second. What we are going to do is, we need all these nodes in the reverse order. So we are going to for the second linked list, we are going to flip it in the reverse order. So now for the second linked list, we are going to change it in the reverse order. So the second linked list we will have would be like, okay, and once this part is done, for the third part we are going to merge this first and second linked list. So first of all, let's see that what are the first and second linked list we have. Okay, so this is the first and second linked list we have. We are going to merge two linked lists until the point when we get the second node to reach to this null value. And how we are going to merge the list is that first we are going to take the node from this first node, first linked list, then we will take the node from the second linked list. Again, we will take a node from the first linked list. Again, we will take a node from the second linked list, and we are going to keep iterating it until the second reaches null. So let's see that in the action. So first node would come from the first linked list, so this would become our first node. Second node would come from the second linked list, so this would become our second node. Again, we will repeat the same process, and in the end we would add this value number 4. And then we realize that we have already reached to the null value for the second linked list, which means that there are no other nodes to be added in the second linked list, which means we would stop adding even from this first linked list, and we would not add all the remaining entries, and this would be our answer, and we can simply return this one. So this is the solution we are going to use. And notice that in this solution we are actually doing 3 different activities. So let's see that how to do each one of them. First of all, we need to find the middle of the linked list, and I have already solved this problem, so you can check out that particular solution over here. Let me quickly go over the solution that I had already proposed. So suppose I have a linked list like this, and if I wanted to do 2 partitions of it, all I'm going to do is I'm going to create 2 pointers. One pointer is slow pointer and second pointer is fast pointer. For the slow pointer, it is going to do 1 iteration to the next element, and for the fast pointer, it is going to do 2 hops to the next pointer. And whenever this fast pointer reaches to the end of the list, this slow pointer would be at the middle position inside the given linked list. So let me show you how. Initially, the fast pointer and slow pointer both would be at the same position. Then fast pointer would take 2 jumps and slow pointer would take 1 jump. So fast pointer would reach over here and slow pointer would reach over here. Again, both of them are going to take subsequent jumps. So slow pointer would reach over here and fast pointer would reach over here. Now again, slow pointer would take 1 more jump, so slow pointer would reach over here. But if fast pointer takes 2 jumps, we already reached to the end of this list, which means that whatever the position of the slow pointer is, this is the part where we need to do a partition, and this would be the middle of the linked list. Next thing we need to do is that we will need to reverse the second linked list. So suppose we are given a linked list like this. So I have already solved this problem as well. You can check out that solution over here. And the idea is that we are going to have two different pointers. One pointer is previous pointer and second pointer is current pointer, and at any point we are going to have the current pointer point to the previous element. So which means because this is a single linked list, all the nodes are pointing to the next element rather than them pointing towards next element. We are actually going to have any single node point to its previous element, and then this would become our head, and then we would have reversed the linked list. So let me quickly show you how. Initially we would have our current pointer over here and our previous pointer over here. So now right now this current dot next is pointing to the next element. So first of all we are going to create a temp variable, and in this temp variable we are going to store the value of this current dot next. So current dot next we stored. Okay, so temp variable is currently over here. Now we are going to have this current variable which is pointing to this next element. Rather than pointing it to next element, we are going to have it point to this previous element. So now this 4, rather than pointing to this 5, it is going to point to this previous element. So this would be null in this case. Okay, and now once this is done, we are going to have this previous pointer jump to the current pointer. So now this previous pointer would come over here. So this is the previous pointer because we have already updated the value of this value number 4, and then the current pointer we are going to take its value from this temp variable. So current pointer would also end up over here. So this would also become the current pointer. Once we have this done, now in the next node we are going to repeat the same thing. So first of all, this temp variable we are going to jump it to the next element. So this would become the temp variable. Again, for the current variable we are going to point it to the previous element. So now this 5 is going to point to this node number 4 rather than pointing to this node number 6. So we are breaking up this connection. And then for the temp for the current variable we are going to flip it to this temp variable. So again, current is going to be ending up at this position. So this is where current is and this is where temp is, and then we will update the value of the previous node as well. So this is where the previous node is. So once this is done, again we will repeat the same process, and then we will point when the previous element reaches over here to the last node, we are going to return this as the head. So in the answer we would have reversed the original list. So we would have a linked list like this, and then once this is done, all we need to do is now we have two separate lists. We will need to merge them. Okay, so for the merge of two linked lists, you can check out that solution over here, and let me quickly show you over here as well. We will start taking one node from each of the given list, and first node would be node number 1, second node would be node number 6, then third node would be node number 2, and next node would be node number 5, and then we will take node number 3, and then we will take node number 4 from this list. And now we realize that the second dot next is actually null, which means that now we don't need to take any more nodes from any other linked list, and we can, whatever the answer is, we can simply return this as our answer, and this would be the final solution that we are going to use. So let's see that what would be the time and space complexity in this case. So for the time complexity, we are actually doing three different things. So first thing we are doing is that we are actually splitting the linked list in two parts. So that takes big O of n by 2 time. Plus second thing we are doing is we are reversing the linked list, which takes big O of n time, and third thing we are doing is we are merging two linked lists which take big O of n time. So in general we can say that we are doing big O of n work, and in terms of space complexity, we are actually using an additional linked list, this second linked list, to store the values, and over here we are actually storing like half of the nodes, which means that we will require big O of n by 2 additional space. So generically we can write this as big O of n as well, and this would be the time and space complexity. Let's see that what would be the implementation. First of all, we are going to check that whether the given head is equal to null. If that is the case, we can simply return immediately. And if that is not the case, we will start with our implementation. So first of all, we are actually going to find the middle of the linked list. So let me create two list nodes for that. Now once we have our slow and fast list nodes, we are going to run a while loop. That while either fast is equal to null or fast dot next equal to null, we will move slow and fast pointer up until that point. Once this is done, we will have a new linked list starting from the slow endpoint, and we will have to reverse that linked list. So in order to reverse the linked list, we will need a previous node. So we will create a new list node called previous, and we will assign it to the value null. We will also have a current node, and we can initialize it to the value of slow, and we will have a temporary node. Now we will run this loop while the current is not equal to null. So first of all, we will store the value of current.next into temporary variable. And after that, we will exchange the values of previous and current node. So current.next will get the value of previous node, and previous node will come at the current node, and current node we will need to move one step forward. So we will assign it to the temp node, where we initially store the value of the previous current.next. And after this second loop runs, we should have our second list, the slow list that we created, to be reversed. And now all we need to do is merge our first list and our second list. So let's create a couple of list nodes, and we will create a list node called first, and we will assign it to the value of the head. And we will also create a list node called second, and we will assign it to the value of the previous node. We will run a loop that while second.next is not equal to null. So over here we will need to take the values from the second node and put it behind the first node. So we are going to use the temporary variable for that. So first of all, in the temporary variable, we are going to store the value of first.next. And after that, for the first.next value, we will take a value from the second node, and for the first node we will get the value of whatever the temp value we had already stored. And after that is done, we will repeat the same process for the second node as well. So first of all, we will create the temp to setup as second.next, and then we will have second.next to point to the first node, and in the end we will have second node point to the temp node. And once that is done, our code should be working as expected, where we would have updated the value of this original given list node. In this case, we don't have to return anything because the return type is void. We only need to update whatever the given input is. So let's try to run the code. Okay, seems like our code is working as expected. Let's submit the code. And our code is actually pretty efficient, and it runs faster than most of the other Java submissions, so which is pretty good thing to do. I would be posting this in the comments, so you can check it out from there. Also on the GitHub, I have created a repository of all the questions that we have solved so far, and I have made it public so anyone can access it. I will be posting this link in the comments as well, so you can check it out, this link, and it can be helpful to a lot of other people. So far we have around 60 to 70 questions, and we are growing it by the day. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do middle of the linked list problem, and this problem can be a great problem to start any technical interview. And this problem has been asked by a bunch of top tier companies like Amazon, Apple, Facebook, Google, Microsoft, Goldman Sachs, Bloomberg, and JP Morgan. So these are some of my dream companies, so that's why I'm making these videos. I hope you also enjoy them. So this is a LeetCode easy problem, and basically we are given the head of a single linked list, and we need to return the middle node of the linked list. We are also told that if there are two middle nodes, we need to return the second middle node. So let's try to understand this with the given example. So over here we are given an example where we are given 5 different nodes. So 5 nodes is odd number. So basically we can determine that, okay, the middle number in this case is going to be the exact number that is at the third position. So we need to return this one as our answer. Meanwhile, inside the example 2, we are given a linked list with 6 elements, and since this is an even number, there can be 2 different nodes we can treat as the middle nodes, 3 and 4. And we are told that if there are 2 middle nodes, we need to return the second middle. So in this case, we will return the value number 4. And it is pretty trivial to understand the problem statement. Let's see that what could be the different approaches. So suppose we are given an example like this, and we need to find that, okay, what is the middle value of this given linked list. The question is that in order for us to find the middle value, first of all, we need to find that what is the total length of this given linked list. And in order for us to find the length, we will have to iterate over this given linked list. That is a given fact, right? But the thing is, only when we find out the length, it is not pretty easy to get the middle value. Why? Because this is a single linked list. So even over here, if we reach and if we iterate through all the values and we find that, okay, the length in this case is going to be 7, so the middle element is going to be length by 2, which is going to be the element located at position number 4. And in this case, still, if we want to attain this position number 4, we will again have to iterate over all the elements to get this value. Why? Because this is a singly linked list. So if we want to now we want to address 2 issues at once. First issue we want to address is that we want to find the length, and second issue we want to address is that we want to find the length in a once we know that what is the length and what is the middle point, we need to find the middle pointer immediately. So one solution that comes to our mind is that we can actually create an array, and we are going to initialize this array with the value 100. So you will ask that why did I choose this value number 100 and why not anything else? Because inside the given input, we are actually told that there is a constraint that the maximum number of nodes we can have is going to be 100. So that's why I chose 100. Now once we have that, we are also going to have a variable called length, and we are going to initialize it to 0, and every time we hop on to one element inside the linked list, we will do length plus plus, and we are going to repeat this up until we reach to the null element. And apart from updating the length value, we are also going to add whatever the node we iterate over inside our array as well. And how it will help us, let me just quickly show it to you. So suppose our given array, so these are the index values. Let's start adding the actual list node values. So first of all, we are at this position, so we'll add value number 1, then we will do a length plus plus, so this becomes 1. So then we will add value number 2, and this would also become 2, and eventually we would have added all the values, so our length would become 7, and over here we would have added all the values. Now we have added all the values, we need to return the middle value. So middle value is actually quite simple to get. All we need to do is that for this particular array, we need to return the value located at whatever the length divided by 2 place is. So in this case, the length is 7. So 7 divided by 2 is actually going to be 3. Why 3? Actually it becomes 3.5, but we are going to use int, and we are going to use floor function. So we need to return the value located at the third index, which is this one. So this is the third index, and the value is 4. So a of 3 in this case is going to be 4. So we will return this 4 as an answer, and this would be our solution. And now you will ask that, okay, rather than in this case we had odd numbers, what if we had even numbers? Even if we had even numbers, even if we only had, let's say, 6 elements, so over here the length would be 6. So if we do 6 by 2, the value is going to be 3, and even in this case we will have to return the element 4. Why 4? Because remember that if we only have 6 elements, we would have 2 middle pointers, and those 2 middle pointers are going to be 3 and 4, and we need to return the second middle pointer, and which is going to be 4. So this can be our solution. This would work perfectly fine, no issues with that. But this will only work just for the sake of solving the LeetCode problem. There are a couple of issues with that. First issue is that we are choosing this value number 100, which we should not choose, because there can be million entries. Your interviewer is going to grind you over it. Second issue is that we are using this additional data structure array to solve this problem. Like, let's see the time and space complexity for this one. So the time complexity in this case is going to be big O of n, and the space complexity in this case is also going to be big O of n. And your interviewer is going to ask you that, can you solve it in better time and space complexity? And the answer is yes. So let me quickly show you how. Okay, so we are going to use the same example and we are going to see that what would be the better approach. Like in order for us to find the middle pointer, what we need to do, we need to somehow reach to the end of this given list, and after we reach the end of the list we need to find that okay, what was the middle point, and whatever the middle point we'll need to return that. So the question is, do we really need to use an array for this one? And the answer is no. A better approach is something which is much more beautiful and very intuitive solution, which is two pointer solution. We are going to have two pointer. One pointer is called fast and second pointer is going to be slow. Initially for the fast and slow pointer, we are going to start at the initial position, and both of them have a special property. So slow is going to do one iteration, meanwhile fast is going to jump by two steps, and we only need to do this until fast reaches to the null or fast.next reaches to the null. The moment it reaches to this point, whatever the value of slow pointer is at would be the middle point of the given list, and we need to return that. Confused? Let me show it to you how it would work. So first of all, let's just create two parameters, fast and slow, over here. So this is a fast parameter at the top, and I'm also creating a slow parameter at the bottom. Now let's start doing the jump. So fast is going to do two jumps at a time. So fast will come over here. At the same time, slow is going to do one jump at a time. So slow will reach over here. Again, fast is going to do two jumps because fast is not null or fast.next is not null. So fast will reach over here, and slow is going to do one jump. So slow is going to be here. Again, fast is going to do two jumps. So fast will end up over here. Slow will also do one more jump. So slow will reach over here. Now, if we check at this position, fast is not null, but fast.next is actually null. So because this is null, this would be our terminating case. So the moment we reach that okay, fast.next is null, fast pointer cannot go anywhere further, which means whatever the position of slow pointer is, that should be the middle of the given linked list, and which is the case over here, that this value at slow pointer is actually the middle of the list, and we simply need to return that. We don't need to do any additional work, and this is a very beautiful solution. If we see the time and space complexity in this case, the time complexity is actually going to be big O of n divided by 2. Why n divided by 2? Because notice that this fast pointer actually do two jump at a time, so we will reach the end of the list quicker. But the thing is, overall in general we can mention this as big O of n. And in terms of space complexity, all we are doing is just keeping track of couple of pointers, and that takes constant space, so it would be constant space algorithm. So this is a very optimal time and space complexity compared to our previous approach, and let's see the solution. So we are going to initialize two parameters, slow and fast, and for both the parameters we are going to put the first value as head. Now we need to iterate over the given list node until we reach that either the fast node is null or the fast.next is not null. Okay, if this is not the case, we will all we need to do is just update the value of slow pointer and fast pointer. So slow would be slow.next, so it will do one jump, and fast would be fast.next next, because fast pointer is actually doing two jumps. And once this loop ends, we simply need to return whatever the value of slow list node is. And let's try to run this code. Okay, seems like our solution is working. This is very few lines of code, so nothing to worry. Let's try to submit this. Okay, our code actually runs pretty fast. It's pretty efficient. So I would be posting this in the comments. You can check it out from there. Also, I have created a GitHub repository where I have posted the solution of all the problems that I have done so far. So you can check it out over here as well. This is growing by the day, so this would be helpful for a lot of people. I would be posting this link in the comments as well. My aim is to empower every single person to be better at technical interviews. Keeping with that goal in mind, today we are going to do a very interesting LeetCode problem called Flatten the binary tree to linked list problem. And if we see some of the popular companies who have already asked this question, there are companies like Amazon, Google, Facebook, Microsoft, Apple, Bloomberg, Uber, Goldman Sachs, ByteDance, and Lyft. So that's why I am paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode medium problem and also a very well-liked problem. Basically, we are given the root of a binary tree and we need to flatten this tree into a single linked list. Okay, so this is the whole problem statement. Now the question is, how do we actually flatten it in the linked list and what are the rules for it? So the first rule is that the linked list should use the same tree node class where the right child pointer points to the next node in the list and left child pointer is always null. So what does it mean by this definition? Suppose we are given a tree or binary tree that looks like this in the example. Basically the linked list structure would look completely different. It would look something like this, where all the nodes are always on the right side and nothing or the left child is always going to be null. So it is going to be a one-sided tree basically. The second condition we are asked is that the linked list should be in the same order as a pre-order traversal for any binary tree. So the question is, what does a pre-order traversal means? Suppose this is the tree that we are given the input. If we want to do a pre-order traversal, the rules for pre-order traversal is basically first we iterate over the root node, then we iterate its left child, and then we iterate its right child. So as long as the left child exists, we will keep going in the left direction. Once left child is no longer existent, we will go for the right child, and always we will first iterate the root child. If we do that, basically in this case, the pre-order traversal is going to look something like this. So first we are going to iterate to the root node. So root node is 1. Okay, so first we are going to visit 1. Then again left child. So left is also 2. So we will visit 2. Then again left child 3. So again 3. Now we do not have any more nodes below this one. This is null. So because this is null, now we will see that whether its root node had any right nodes or not. And yes, it does have a right node. So we will start visiting the right nodes again. And then we will keep on repeating the same process. So now we have visited everything on the left subtree. So now we will start iterating on the right subtree. So if we go over here, now we will visit node number 5 and then node number 6. So this would be the pre-order traversal. Now the question is that for the given input tree, what should be the answer look like? So we have to consider a couple of items in order to generate the answer. First one is that it has to be the pre-order traversal, and then it has to be like a one directional tree. Okay, so keeping with both things in mind, the tree structure in the answer is going to look something like this, where the first node is going to be 1, and then the second node is going to be in the pre-order traversal 2, but 2 we are going to mark it on the right side. The next one is going to be 3, so again 3 is also going to be marked on the right side. And if we keep on repeating the same process, basically this is the answer tree that we need to return, that represents the flattened binary tree that we are given as the input. So this is the binary tree and this is the linked list version of it, and that this has been flattened. Now in terms of like input and output, basically the input for this one is going to be something like this. So basically this is going to be the original input that we are given that represents this binary tree, and after flattening it, the tree is going to look like this, and we need to return an output that looks like this. So basically this is the whole ask of the problem. Now let's see that what is the approach we can take. Okay, suppose this is the most basic input or most basic binary tree we are given. Now in any tree problem, what we are going to do is we will try to see that what would be the solution for this one, and then using a recursive approach we can actually solve it for much bigger problems, because that is common property in tree. If we see most basic structure of a tree, basically it has a root node. This root node currently has a left child and it also has a right child. Okay, so let's mark some values so it makes sense for us to understand. So this value is 1, this is 2, and this is 3. Suppose this is the given tree. Now if we want to flatten this one, we will have to keep track of two items. First one is that it has to be the pre-order traversal. So pre-order traversal, we already know the value is going to be 1, 2, and 3 in this order. Second thing we have to keep track of it is that it has to be a flattened version and everything in just one directional. Okay, so what does that mean? That structure has to look something like this, where all the three nodes are just the right childs, nothing on the left child. Keeping with these two items in mind, the answer in this case is going to look something like this. And notice in this case, the root node remains the same. This left child is come as the first right child of this root node, and the right child of this root node or this node 2 becomes this node 3. So basically, if we just see what are the actions we did in order to generate this answer, First of all, we took this left child, and currently this left child does not have any children of its own. So there is no like left child over here or right child over here, right? But if we see in the answer, currently for this left child or this node, it has a right node, and that right node is whatever the previous root's right child was. So what we did is, first of all, for the existing left child, we had the left child dot right. So right child of this original left child, which was originally null because it does not have any values over here. So this value was originally null. We marked it as the root dot right, and which we can see over here that in this case, this root dot right, this is this right child. We mark it over here. Okay, so this is one thing we did. Second thing we did is, in the answer, currently this root dot left, this left node actually has some value over here, but in the answer this left child is null. So we will also do that. So currently this root dot left is going to be null. Okay, that is also the second thing we did. What is the third thing we did? The third thing we did is that currently this root dot right, this value is pointing towards the right child, but rather than pointing it towards the right child, now we are pointing it towards the left child, which we can see over here clearly. So the third thing we are doing is that root dot right, that was originally pointing towards the right pointer, now it is pointing towards the left child, and that's it. That is the whole logic to solve this problem. And how we have been able to generate this, let's try to see it for a bigger version, and we will keep on repeating the same process, these three items. So now we will try to apply these three rules for this given tree, and this is the original bigger version. So first of all, we will recursively try to find a smaller subset. We will do these three things and keep on repeating the same process until we find the full answer. So first, if we start iterating from this root element, first of all, what we can see is this is one of the candidate for the left subchild where we can actually apply these three rules. So let's apply that. So after applying these three rules, basically for this particular portion, this 2, 3 and 4, the answer is going to look like this 2, 3 and 4. And if we just mark it over here, we will get a tree structure that looks like this. Now in this case, now this is the perfect candidate because we do not have a full subtree. So basically we have this left sub portion, we have this right sub portion, we have this root node. And again, we are going to apply the same logic. So if we apply the same logic in this case, again, second recursion, what we need to do is for this particular left node, basically we will need to see that what is the rightmost tail, and the rightmost tail is 4. So this 4 needs to point over here, and this 1, rather than pointing to this 5 on the right child, this needs to point over here, and the left child is going to be null. So this is all we need to do. So if we apply these three logic, basically first of all, we are going to have our root node 1 as the right child. We are going to point over here rather than pointing towards this 5. So if we point towards this portion, we will get the values 2, 3 and 4. And if we see, currently this 4 is now pointing towards this value number 5. So that we are going to mark over here, and basically we are going to have values 5 and 6 in this case. And if we see, the left portion is always going to be null for every single one of them, and this is the answer we need to return. I know I have not drawn this properly, so let me just do it properly. And this is the most simplest approach. What we did is we first of all try to find the solution for a smaller subset. We find the base cases and the rules. We applied those rules to a bigger case, and we, using recursion, we are able to generate this answer. And this is a very simple answer to understand. If we see time and space complexity, in this case the time complexity is actually going to be big O of n, and if we see space complexity, the space complexity is also going to be big O of n, because for recursion it is going to need to store some runtime stack. So first of all, we are going to create a helper method that we can use as our recursive method. So let's just do that. Now in this helper method, first of all, we will check that if the given node is null, we can simply return null. Second thing we can check is that if the given node is like a leaf node, which means if it does not have any left and right child, then we can simply return that node as it is. Now we will have to find the leftmost tree node for any subtree. So we will have to create a new tree node called left tail, and we are going to call the recursive function again. And same way we will also have to find the rightmost tail. So we will also do the same thing and we will call the recursive function again. Now will come the meat of our logic. So first of all, we will check that if the left tail value is not null, if it exists, then we will have to put those three conditions that we discussed earlier. First of all, for this left tail value, which means the leftmost value of any subtree, we are going to mark its right child to point towards the node dot right. Then for the existing node dot right value, we are actually going to point it towards the node dot left. And in the end, the node dot left value that we currently have some value pointing towards, we are going to mark it as null. Basically, that's it. Now in the end, we need to return the right tail or the rightmost element. So we are going to check that if the right tail is equal to null, then we need to return the left tail. If it is not null, we will return the right tail. And now all we need to do is from our main method, we will have to call the flatten tree method with the first root node. Let's try to run this code. Seems like our solution is working as expected. Let's submit this code. And our code runs pretty efficiently compared to a lot of other solutions, so which is great. I will be posting this solution in the comments so you can check it out from there. Thank you. And my aim is to empower every single person to be better at technical interviews. Keeping with that goal in mind, today we are going to do a very interesting LeetCode problem called reverse nodes in a K group. If we see some of the popular companies who have already asked this question, there are companies like Amazon, Microsoft, Apple, Bloomberg, Google, TikTok, Facebook, ByteDance, Uber, Snapchat, Paytm, and Tesla. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode hard problem and also a very well-liked problem on LeetCode. Basically, we are given the head of a linked list and we are also given another value, integer value called k. Now, based on this given head of the linked list, we need to reverse the nodes inside the given linked list k at a time, and we need to return the modified list. There are also some additional parameters given which states that basically if we have the number of nodes that are less than k, we do not need to reverse them. Let's try to understand this with an example. If we see in this case, we are given a linked list and we are given the value k is equal to 2. Now if we understand the problem statement, basically we need to reverse the nodes inside this given linked list k times at a time. So in this case, 2 nodes are given, so we are going to reverse 2 nodes and then keep on repeating the same process. So the idea is, first we are going to reverse these 2 nodes, whatever the answer is we will store over here. Then we will reverse these 2 nodes and again we will store that answer over here. And since this one is only one node and we are given the value k is equal to 2, we are not going to change anything over here. So if we see the answer in this case, basically if we just reverse these 2 nodes, the reverse node is going to look like this, 2 and 1. Then we have the nodes 3 and 4, which are the two next k nodes or next 2 nodes. So again we are going to reverse them, and since this is only the single node, we will not reverse them. So this is going to be the modified reverse list that we need to return as the answer. If we see, basically we are reversing k nodes at a time, and at any point we identify the nodes less than k, we do not do anything. Now the most basic thing we can do to solve this problem is, first of all, we need to check for the edge case scenario. The edge case scenario is that if the given number of k is actually greater than the number of elements present inside our linked list, if that is the case, basically we don't need to modify the given input linked list and we can return the answer as it is. Why we can do it? Because the given k is equal to 6 and we are being asked to reverse k nodes. But in this case, since k is greater than the given number of nodes present, there is no way for us to reverse all 6 nodes, which means we don't need to modify the answer as at all, and we can simply return as it is. Now let's try to think about some logical scenarios. Suppose our given value is equal to k is equal to 2, 3, something like that. If that is the case, what is the approach we will take? The approach is quite simple. First, we will take these 2 nodes we will do the reversing function. For all the remaining ones, we will repeat the same process after we are done reversing these two elements, which means first we will do like a reversing function, and then for all the other nodes, so currently this 1 would be pointing towards this 3. Now for this newly created list, we would be able to repeat the same process. If we repeat the same process, now this time we will reverse these two nodes. And again, if we keep on repeating the same process, we will only be left with just a single node which only contains one value, which is again less than the value of k, which means we don't need to change this portion. If we see logically, this becomes a very good candidate for a recursive approach. Why recursive approach? Because essentially every single time, first of all, we were considering all of these 5 nodes to do like k equal to 2. Once we are done iterating these 2 nodes, we can get rid of them, and now our input shrinks to the 3 nodes, and then again we will repeat the same process, and then again if we get rid of these 2 nodes, we only are left with just a single node, and then we need to repeat the same process, which means recursively this is going to be a very beautiful approach to solve this problem. Now we already know the overall framework on how to solve this one, but one key important piece of information missing is the reverse function that we need to perform. In order to perform the proper reverse function, first let's identify that what is the methodology we are going to use. Okay, now let's try to figure out that if this is the given input linked list we are given, we are simply trying to reverse this whole linked list. We are not currently considering about the k values because we already know the solution. So if we want to reverse this entire linked list, what is the approach we can take? Well, let's try to see that what are things we have. We currently have a head pointer that points to the first value inside our linked list. Now since we need to do the reverse linked list, basically the reverse linked list is going to have a new head, and this would be the head of the reverse linked list. So we will also, first of all, we need to create a new node called new head, and initially new head value is going to be null. So let's just create a new head. I'm going to mark it as nh, and currently the value is null. Okay. We will also need to find some way to iterate over the given input existing linked list. For that, what we can do is we can create a pointer node, and this pointer node, we are going to initially assign it to the value of the head pointer, and then we will use the pointer node to move towards the next values. So let's just create a new pointer node in this case. After creating these two values, we will need to at any given position keep track of the next node, because for the pointer node, we will need to iterate to the next element. At the same time, using the pointer node, we are going to manipulate the values of the new head variable because we are reversing the linked list. So we will need to create a new variable called next node, and initially the next node value currently is null. Just understand for the sake of understanding that this is null. And now we don't need the head node. So after initial setup or initially setting up everything, let's see that what would be the approach to reverse the given linked list. Okay, now first thing we are going to do is, since we need to keep track of the next node, we will first assign the value. So we will keep the next node to be the pointer.next. Okay, we set up the value of next node to be pointer.next. So at this position, the next node is going to be here. Okay, now we also need to keep track of the value of pointer.next. But the thing is, since now we are trying to reverse the linked list, basically the pointer.next is going to point towards the new head. So let's mark that. So pointer.next should move towards the new head. Okay, so currently the new head value is null. Keep it that way for now. Now we need to update the value of the new head. So for the new head is going to be the existing pointer we are at. So existing pointer currently is 1. So in this case, the new head was going to be the value of 1. Okay, so let's just mark this value. So new head is going to be the existing pointer value, and in the end we need to move this pointer to the next element. How would we be able to do it? Using this next node, because we already updated the value of pointer.next. So we will need to move for the pointer to the next value, which is going to be pointer is going to move to the next node, so nn. And this, using these steps, we would be able to reverse this linked list easily. So now after the first iteration, this is the current setup we have, that new head is located at 1. currently the pointer is located over here and new node is also here, but during the next iteration the values will be updated. So now let's update the values again. So now, okay, new node becomes to the next value. So this is going to be our new node. Now at the same time, pointer.next points to the new head. So currently this pointer 2 is pointing towards 3, which rather than pointing towards 3, now this 2 is pointing towards 1. So we are going to have a configuration. So currently the new head value is 1 and we are going to have 2 point to the 1. This is the current logic we have. Okay. At the same time, new head is now going to move towards pointer, which means that rather than new head having the value of 1, it is going to have the value of 2. So let me write this in a little bit separate manner. So if I do that, basically currently the new head is going to be the pointer value, and the pointer dot next we already define it to be the previous new node, which is going to be 1. Okay, so now this is the setup we have. And also now pointer moves to the next node. So next node is 3. So now pointer again moves to the next node. So pointer is here, next node is here. Again, if we repeat the same iteration, basically the next node is going to be pointer dot next. So this is going to be the next node. Now pointer dot next is going to become the new head. So pointer dot next is currently pointing towards the value number 2. Value number 4, but rather than pointing towards value number 4, pointer dot next is now going to point towards value number 2. At the same time, new head is going to become pointer. So now let's just make this changes as well. Now in the end, we simply need to move pointer to the next element. So now pointer will move to the next element. And in the end, if we repeat the same process again, basically the next node will end up at null and we will have the new head to be value number 4. And since the next node is null, we cannot do anything. So we can break out of the loop here, and whatever the next head is, we can simply return that. But at the same time, we reverse the given entire linked list, and this solves the major concern of our problem. So now we already know that how to reverse nodes. Okay. So after understanding all the small pieces, now let's see that what would be the optimal solution. Basically, for the optimal solution, we have two options. First option is that we use the recursive function, and then things becomes much easier for us. Basically, we take these two elements, we apply the recursive function where we basically reverse them, and after reversing, we update our value and again repeat the same process for these three remaining items. Again, we reverse these two items and then we keep the last item. And then basically using the recursion and the reverse function, we would be able to solve this problem quite easily. Now for the recursive approach, if we see time and space complexity, basically the time complexity is going to be big O of n, because we need to iterate over the given input twice. Why twice? Because first we need to check that whether for the given input, if the given value of k is greater than or not, or less than or not. And then secondly, we need to do it for the reversing the k nodes. If we see space complexity, the space complexity is going to be big O of 1, where big O of n, where we will use n space for the recursive stack. So the next question your interviewer is going to ask you is that rather than using the big O of n space complexity, can you solve this problem in big O of 1 space complexity? So that is also very simple to do. Basically all we need to do is that at any given position, first we will try to see that whether the given k elements exist or not. If they exist, then we will simply reverse them, and we can simply use like couple of while loops and do this iteratively. And iterative, the logic is going to remain the same, but first we are only going to check that whether the number of k elements are present or not. If they are present, we are going to simply apply our reverse function, and after keep on reversing the values, eventually we would be able to find our answer as needed. And iteratively, this is the answer we need to return. If we see time and space complexity, in this case, the time complexity is actually going to be big O of n, and the space complexities in this case is going to be big O of 1. Now for the coding solution part of this particular reverse nodes and k group portion, actually I made a blunder before. I recorded the whole video explaining the code, but I forgot to use my microphone, and that's why I didn't record any of the voice. Now I'm not going to do the whole thing again. I can just go through the code and then I'll post this code in the comments, and also I can post this code in the GitHub repository that I have created and provide links for both of them. So basically you would be able to see the code. Now in this particular solution, basically we are using the iterative approach by which we will have a better space complexity, and definitely we need a way to reverse a linked list. So I'm creating a helper method that takes in any list node as an input and a k value and return the reverse linked list new head. So these are all the steps that we discuss in the explanation part of the video, and we keep on repeating the same process, and this is just the helper method. Okay, now let's move on to the main method. Now inside the main method, first of all, we are defining a few of the variables that we need to keep track of different things. So basically we have a variable pointer that will iterate over the given entire list. We are also keeping track of a k-tail variable, and what this k-tail variable does is that whenever we are done iterating like any set of k nodes, and we are planning to go to the next step. So if we see on the left side of the screen, suppose we have done iterating reversing this 1 and 2 node, which means we still have nodes 3, 4 and 5 to process. So k-tail would be pointing towards this node number 2, and we would be able to do certain things with that that we will see next in the code. Now first of all, we are going to initialize a while loop that while the pointer is not equal to null, which means this is the loop that runs over entire given linked list. Now inside that, first of all, we have a counter and we also have pointer located at the head position. We first check that whether the current count, if that is less than k, we will move the pointer towards the next element and keep on updating the value of k. And now we would be at the position if the count is equal to k, which means we are at the position where currently we will need to reverse the nodes that are between those values. So say for an example, initially count would be 0 at this value number 1 and count would be 2 at this value number 2, and basically we need to reverse like these two values. So we will use our reverse function, and after this condition is only there for the first case scenario, because if we see in the output, the head is always going to be the reverse portion of first k nodes. All the other k nodes doesn't matter. So that is why this is to define that what is going to be the new head value. And then this checks that whether the k-tail, if that is not equal to null. If that is not equal to null, which means that the k-tail value is actually going to point to the new reverse node value, and that is why we are using the k-tail variable. And in the end, we just update the k-tail pointer and also the head pointer and keep on iterating the while loop. So basically using the combination of these two, we are able to solve this problem. And in the end, we are simply returning the new head. So we will check that if the given new head is equal to null, if this is the scenario, this will only happen if the given k is actually greater than the number of values present inside our linked list. And in that case, we simply need to return the old head. And if the new head is not null, we need to return the new head value. And this is the whole solution. I hope the solution makes sense. And now let's try to run this code. So our solution seems to be working. Let's submit this code. And if we submit this code, our solution actually runs 100% faster than all the other solution, and that is because the runtime is actually 0 millisecond. And even if we see in terms of space complexity, this is really good. So this is a very good solution. Again, I would be posting this in the comments, so you can check it out from there, or you can check it out from this GitHub.